All right, hello grade 12s. We're going to be starting our first lesson, quote unquote lesson in trigonometry. We're going to be kind of mostly looking back at grade 11 material and kind of refreshing ourselves. We're going to start with our graphing journey here. We're going to look at sine x, cosine x. Those are some familiars. And we'll test the waters a little bit with the tangent function. And at the very end, we're going to also look at the reciprocal versions of each of these. Okay, so just to start here, I'm going to ask you to pause the video, grab a calculator, actually see how much you remember. Definitely you should be able to populate 0, 90, 180, 300, and 360 just from memory. Did I circle the right ones? Oh, not 300. 270 for sine and cosine. In fact, those are the main ones we're going to ask you to memorize going forward. The other ones you should be able to generate some other way. We'll talk about that later. So pause the video. I want you to try out 1 and 2 on your own. Complete the tables, and if you want, graph them accordingly. We'll pause a little bit because tangent's slightly different. Okay, so pause the video, try it out. Okay, and hopefully you had some success there, literally just plugging into a calculator at this point. But some things to kind of recap here. For the sine x function, hopefully it kind of like came back a bit. Sine x is the function that begins at the equation of axis at 0, goes up to its maximum 1, down, back to the equation of axis, then to the minimum, and then back up for a full period of 360 degrees. Actually, shoot. I was kind of hoping to do... I'm not going to do that. I'll change it to a different color later. For the cosine function, in its similar sinusoidal kind of form, would start from the maximum down to the equation of axis, then down to the minimum at 180, back up to the equation of axis 270, and up to its maximum at 360. So hopefully somewhat familiar. Those two have not really changed. So you know what, let's just kind of copy these in and let's graph them. I'm going to ask you one more time again on the next sheet. You have it with you. I'm going to put my coordinates here. And I'm going to put down those coordinates. Okay, so meet you in a couple of minutes. Unpause the video when you are done graphing. Okay, welcome back, and hopefully this is the graph you got. Well, the picture of the graph anyway. We can also, do a couple of things here. Because for sine x, well, x is an element of reals. We can extend this graph forever to the right, forever to the left. We drew one period over here. We can extend the graph to the left now. Negative half, negative 0.86. And negative 1, negative 0.86 again, and then negative half over here. And we'll get the following. Okay, beautiful. And now we have our sine x graph right here. Okay, we're going to rinse and repeat. We're going to grab the table for, oopsies, for cosine. And we're going to grab it. And we're going to paste it over here. We're going to draw a picture, draw the graph for cosine this time. And, revisit an old friend here. Okay, pause the video, give it a try. All right, once again, no surprises here. In fact, I spoiled it earlier. And once again, because this is a continuous graph, let's also extend the graph to the left. So 0.87, half, 0, negative a half, and negative 0.87. And we'll complete our cosine graph like the following. Okay, let's slow down a bit now for the tangent graph. For the tangent graph, in fact, we're asking you to fill it up, quote unquote, twice. Hopefully, not on alarm bells, but some memories are kind of trickling back here. The reason why we're doing sine x over cosine x because of that old identity. There's no such thing as tangent on its own. Tangent itself is built up of two functions in a reciprocal, not a reciprocal, it's a rational function. We have one over the other. So there are two ways to use it. Well, one, we can just use a calculator. But the other one is because we have tables for sines and sine over cos. We could do 0 for the sine value divided by 1 for the cosine value, and we're going to get something like 0 here. And if we ever have 1/2 divided by 0.87. This one is going to be 1 over root 3. And I forget what that value is. I'll come back with it in the after you try that. Okay, go ahead, fill out the table over here. You don't have to fill out both. They're going to end up being the same. But there's something interesting we need to comment on. There'll be a couple of interesting results that you get. Skip those for now. But think about what's happening. Why did you get that weird result? We'll kind of recap that soon. Try it out. Okay. Hopefully that was fruitful. And also, hopefully, you realize there were two issues at 300 and at 90. Why did I say 300? 270 and 90. Those were specifically when cosine x were equal and of 90 and 270 were equal to 0, giving us the denominator was equal to 0. One step further here. Well, in the last unit, we saw when we had a rational function, f of x over g of x, and we saw that the g of x went to 0. One of two things happened here. Either we got a whole or vertical asymptote. Now, once again, pause the video. Think about what that might be. Well, here we're dealing with a vertical asymptote. Well, the way we explained the way the whole was that it was a restriction that was originally there, but once simplified was removed. Sine x and cosine x do not cancel out. They are not the same factor. Therefore, this 90 and 270, that 0 in the denominator, refers to a vertical asymptote. So interestingly enough, the tan function is going to have a vertical asymptote. So there's one vertical asymptote located at 0, one vertical asymptote, sorry, not at 0, one at 90 and one at 270. So let's draw the structures in. So one at 90, that's a vertical asymptote, and one at 270. Let me also copy paste this table in here so we can kind of do this one together. Okay, so let's copy and paste it. Beautiful. Okay, here we go. Alrighty. Okay, so let's put in these values here and get a nice picture of tan x. So tan x is 0. At 30, it's 0.58. So just a hair over half. 60 was 1.73, which is basically 1.75, that location over there. And we can draw something like this over here. And remember, a vertical asymptote insinuates the function is either going to go up to positive infinity or down to negative infinity. I think this is good enough to imply that we're going to go to a positive infinity on the left side of 90. On the right side of 90, we're coming down from negative 1.73, then to 0.58, 0, to 0.58 on this side, and to 1.73 on this side as well. And okay, this one is a little bit more complete. It has like a the whole section drawn out between both of its asymptotes. You will notice it looks very much like a cubic function. And yes, this is an inflection point. Just a cubic functions squished between two vertical asymptotes. Let's kind of draw the rest of this graph and kind of figure out how to extend it as well. At 300, we were also once again at negative 1.73. And at negative 330, we were at negative 0.58 and back up to 0. Okay, we're going to get the following. And if we extended the graph left here, okay, we would see this go down to negative 0.58, down to negative 1.73, and we'd get the following. Let's make it look a little bit nicer, something like that. And yes, we also would have another vertical asymptote at negative 90. Okay, and that is the picture of our tangent function. A couple things to note here. Whereas sine and cosine had a period of 360 where it took to repeat itself, well, between the locations of 90 and 270 is a distance of 180 degrees. Tangent function has a parent function or the original period before it's transformed of 180 degrees. And another thing you see here is visually striking because there's no such thing as amplitude here, where a sine and cosine function are kind of stuck between a max and a min value, like the highest, the crest and the trough of your sinusoidal function. No such thing exists for tangent. Okay, the last thing we were going to discover or kind of want to make a connection with here is the reciprocals for each. There was a reciprocal for sine of x. That was if we do 1 over sine of x, we create a function called the cosecant, CSCX. Think about, okay, using the properties we saw in Unit 3, to help you draw the cosecant function. Do the same with the cosine function, which would become 1 over cosine, which is known as secant of x. And also with tan, if we ever did 1 over tangent of x, we were talking about creating cotangent x, cot x. Okay, give it a try. We will take it up when you unpause the video. Okay, welcome back. Hopefully this is what you got for your cosecant x. Well, if you're wondering how I did it, we're going to look at the next one there. Hopefully no surprises. Hopefully you did okay. Okay, you can use this as a template. You can copy it down, but in case you're wondering about the steps, let's work through it together with cosecant x. With cosecant x, what are we looking at? Well, we want to draw a reciprocal of a function. We have to remember a couple of things here. The old x-intercepts of the function, the original function, becomes the vertical asymptotes of our original. So hopefully those vertical asymptotes didn't surprise you. You're like, okay, yeah, those are because now before it was an x-intercept, but now it is a vertical asymptote because it's a 0 in the denominator. Okay. The other thing we also had, okay, so let's write that down. So if we were going from f of x to 1 over f of x, the x-intercepts of f of x become the vertical asymptotes of 1 over f of x. And the other one is when f of x was equal to 1 or negative 1 or 1, those are the locations that don't move. Those are our fixed points. So we can quickly just highlight anytime it's a 1 or a negative 1. Those are the ones that are going to be the same on f of x and our inverse. Sorry, not our inverse, our reciprocal. Maybe if you want some more points, take a point, like this 1/2 here. If we take the reciprocal of that, that's going to flip and become a 2. So every 1/2 becomes a 2. And okay, we know exactly what's going on in this region. Let's do the same for this region here between 90 and 270. This negative 1/2 becomes a negative 2. We're just simply taking the reciprocal of any location we want. 2 is just convenient for us. And this positive 2 becomes this becomes a positive 2 as well. We'll get a graph like that. And here this becomes 2, negative 2. We'll get a graph like the following. Okay, I shouldn't put my second arrow there. Okay, there we go. Cool. Let's kind of go a little bit slower with the tangent function. So with our tangent function, same idea. Anywhere we used to have a, let's get a different color here. Everywhere we used to have a x-intercept is now a vertical asymptote. Oopsies. A vertical asymptote. What else? Now we may want, just to find some reciprocals here. The reciprocal of 0.58 is going to be slightly under 2, so about there. This one is going to be, you know what, let's find out. What is 1 divided by 1.73? And I'm getting a number like 0.58. Wow, interesting. Oh yeah, of course, they are reciprocals of each other. Oh my goodness, I'm so silly. That goes there. And when this goes off to positive infinity, this thing approaches 0. But because it came from a restriction, we can't actually have it. There's a little subtlety here. Because we're drawing a graph from the reciprocal, we can't actually let it equal. We are going to just leave that as a donut hole there. This one goes here. This one goes down there. So let me just recap again. If you're wondering, how did I get this height exactly? This was originally at a height of negative 1.73. But if we ever were to flip that, 1 over negative 1.73, turns out that does become 0.58, which is the height of the other one. So they have a reciprocal relationship with each other. In fact, I could have filled out the graph. This is 1 over root 3, and this one itself was root 3. Okay, so we'll fill out the rest of the graph that way. Here we go. Here, full. Here, and there we go. We have our graph of tangent x. Well, basically has the same shape. It's just being shifted and reflected. Um, yeah. Okay, cool. And we'll get another one over here. I'm going to be slightly bad and just not do it. Okay, cool. There you have it. The second key skill we need to kind of have at the ready for trigonometry this year is also going to be our special triangles and some stuff about casserole. Here we go. You have to memorize 45, 45. So it's isosceles. These two have to be the same. We'll call them 1 and 1. And by the way, the shortest side on each of these triangles is a 1. And then the opposite of the 1 is a root 2. You can do Pythagoras now to do that one. So here, as long as you remember the shortest side is 1, then we get 60. Now, how do you populate the rest? You can use a little Sokoto if you like, but I just kind of memorize. It's going to be root 3 and 2. Okay, let's actually just grab everything for a second here and just move it. Oh, didn't mean to grab this one. Move back now. Okay, there we go. We are asked to use special triangles to determine the exact values. Ooh, okay, so no rounding. Of the trigonometric ratios. So find the exact value of sine of 60. So it might help us to just redraw that triangle that's pertinent to us. So we're drawing the triangle for 60. We are, what are we looking for? Well, we have to remind ourselves, what does sine mean again? Sine is a ratio of an opposite to a hypotenuse side of a right angle triangle. So what was the opposite side of 60? That's across from the 60 over there. That's the root 3. And what was the hypotenuse on this triangle here? Well, that was the 2 over there. So sine of 60 is exactly equal to root 3 over 2. Okay. Well, not so bad. Let's beef up the example by quite a bit. What if we're asking for cosecant of 135? So first we see a cosecant. We're like, we don't have a cosecant button. Let's kind of switch things around. Cosecant is actually 1 over sine. So 1 over sine 135. Now, the other issue is that this 135 does not really play nice. Let's just get a picture of what 135 looks like. Hopefully you remember how to count degrees or how to count angles. The 0 degree angle is the positive x-axis, and we count positively in the counterclockwise direction. If we want to get negative degrees or measure negatively, we can measure clockwise, and that orientation would be a negative degree value. Okay, so 135 is somewhere between 90 and 180, 135 out there. Just like you saw last year, we could also work instead of the principal angle, 135 theta, we could switch it out with this little fish, alpha, which is the closest acute angle to the x-axis. And in this case, the counterpart to 135 is an angle of 45 degrees. And okay, that makes a little bit more sense. The purpose behind using casserole is to simplify our expression to always work with the special angles. So this becomes sine of 45. Now, it's not quite free. We must remember one additional thing. Well, we have to do an analysis about whether it's going to be a negative sine 45 or a positive sine 45. Now, that's where the cast part of casserole actually comes in. Because 135 was in the S quadrant, sine is the positive ratio there. Therefore, I'm also going to put a manual positive sign to remind myself, okay, hey, this I've already accounted for the casserole and that thing is positive there. Okay, now we're ready to calculate. Well, the sine of 145 is, well, 45 it has an opposite side of 1 and a hypotenuse of root 2. So it's 1 over root 2. Which is, in the end, just root 2, because we're just taking the reciprocal of that thing. Okay, well, we're also going to work kind of in reverse. Sometimes we will be told the value of a sine ratio of an angle. Okay, so some angle theta satisfies this ratio here. Sine theta is equal to negative 0.454. We are asked to find, well, what are the angles between 0 and 360 that satisfy that? So what are the angles that make it work? Here's some steps. Actually, I don't want you to start with step 1 just yet. Let's do a step 0. I like to do this one because you can think about it even before you grab a calculator. Think about which 2 regions will allow us to make an angle produce a sine that is negative. So we want a negative sign. Okay, so let's just write in cast again. Oops, not there. C-A-S-T. Well, let's think about it. For sine to be positive, it would have to be in the all quadrant and the S quadrant. But we don't want that. We want sine to be negative. So let's take those away. So then the only two places it could be is T and C. Okay, but then now the question is like, well, how far into the T and how far into the C? Well, we don't know. That part we do need a calculator part with for. So we're going to find that reference angle alpha by using the positive solution. So even though this was a negative 0.454, we will take the inverse of just positive 0.454. It is possible to work with the negative. However, our solution uses the positive version. Okay, let's grab our calculator. Second function, sine of 0.454. That's equal to 27 degrees, basically. And that little alpha, once again, is the thing that connects your principal arm to the terminal arm in T and C. Okay, last little bit here. Unfortunately, we can't just measure any way we like. All our measurements must come from the 0 over here. So how do we get from 0 to the, let's call this theta 1 in C? Well, to get to theta 1, well, first we have to travel to 180 and then travel a little bit extra than alpha. So theta 1 is the measurement of 180 plus 27, which is 207 degrees. For theta 2, we'll visualize the same journey. Well, to get to theta 2, which was our here, well, we'll first go by 360, but we'll say, oh, shoot, we went too far. We have to go backwards by alpha. So we'll end up doing 360 take away 27 degrees, which is equal to 333 degrees. Okay, let's recap. Well, these types of questions, we are asked to figure out what angles would make a ratio equal to this. The way we'll figure that out is two parts. The first major part is the cast analysis. Where will we find regions of this ratio being positive or negative? Now, remember, cast tells you only what's positive, since we wanted negative results, so not S for sine, not A for all. Everything's positive here. So T and C. Then to find that little alpha, we'll do the inverse function on the positive version of this solution, and then they'll tell us alpha. And the last part is to put it all together. How do we start from 0 to get to each of those terminal arms? We need to find that exact measure between 0 and 360. Well, then we have to just do a little bit of analysis. I think that part's the one that takes a little bit more work. Let's do a different example. Pause the video, try it out on your own, of course. Okay, hopefully you had some success. Let's see how it went. Okay, so we're looking for a cosine to produce a negative result. So once again, let's write C-A-S-T. If we wanted cosine to be positive, then it goes in A. If we want cosine to be positive, then it goes in C. However, we want a negative cosine. So we'll put one terminal arm in S, one terminal arm in T. Okay, and we will quickly also visualize our alphas as being the thing that connects it to the closest x-axis. Okay, alpha is equal to cos inverse of positive 0.53584. What is that? Second cosine of 0.3584 is basically 69 degrees. Alpha is equals to 69 degrees. Okay. And once again, we already did our analysis earlier, S and T. Okay, now we need to find both of those angles. Let's call it theta 1. Let's call this theta 2. Theta 1, how do we get there? Well, we will have to start at 0, and we'll want to go to 180. We can only go to 180 or 360 or 0. So we have to go to 180 first. And then from there, we've gone too far. Look at that. We already crossed over theta 1. So we have to back it up by alpha. So our end result will be 180 take away 69, which is equal to 111 degrees. Okay, let's take that away now. We'll do the same analysis one more time. For theta 2, we have to travel all the way from here to here. Okay, so first we'll have to travel to the 180 mark once again, but that's not enough. We still have not reached that little angle, so we have to go an extra little bit plus alpha. So that's 180 plus 69, which is 249 degrees. And those are your two angles. And by the way, you can quickly double check. do cosine of 111. And hopefully you're going to get that original result back. All right. One more time. Same idea. Quickly give it a shot. Try it on your own. Okay, here we go. For tan theta, we want a tan to produce a negative result. So let's just quickly write down CAST one more time. To get a tan that's positive, T and A. So no. S and C instead. S and C. So let's find our little alpha, little fish, is equal to tan -1. Reference angle of negative 28 point. You know what? I'm going to show you what happens. Let's have some little forbidden fruit here. Negative. What if you put the negative in there? We'll make one quick connection before we end off today. We're going to second function negative 28.636. And we're going to get a negative answer here. Alpha is equal to negative 87.999. So actually negative 88. Negative 88 degrees. So can you guess what that means? It means that starting from here, we could actually measure our angle. Alpha equals negative 88 degrees, and that's pretty done. However, the original question wanted us to only have angles between 0 and 360. This is our domain. Theta element. Okay. So actually, okay, if we actually did it the right way, I don't want to say right way, our way, we would have gotten instead a positive 88 degrees. Okay, so we're kind of going to ignore the signage on that there. All right, so we have alpha here, we have alpha here as well. Okay, now how do we make it to both of those angles? To make it to this one out here, we'll go by 180, but that's too far. We have to go back by alpha. So theta 1 is equal to 180, take away alpha. This is the one in the S quadrant. Which is equal to 180 take away 88, which is equal to 92 degrees. Theta 2, what's that going to look like? That's going to be going around a full 360 and saying, oh shoot, that's too far. That's 360 take away alpha once again, which is equal to 360 take away 88, which is, if you take away 80, that's 180. No, 280 take away 88 again, 272 degrees. Okay. Well, that's it. Welcome to trigonometry.